Welcome, my dear students. In the last class, we proved the first isomorphism theorems and the fundamental theorem of homomorphism, and we discussed some examples, and then using this fundamental theorem of homomorphism. And now, in this class, we discuss about the second isomorphism theorem. And in the second isomorphism theorem, we take a G be a group, and H is a subgroup of this group G, and N is a normal subgroup. And then we have a set. Hn is the in the form of this Hn. H is the element of H, and N is the element of N. And then this is a Hn is a subgroup of this G. So this means we can say that this Hn is defined in this is a again is a subgroup of a G, and intersection H intersection N is a normal subgroup. So H intersection N is nothing but is equal to, you can say that is a normal subgroup of H, and we can say that H over quotient of H H intersection N is isomorphic to quotient of Hn over N. Now this is clearly we show that this is N is a normal subgroup of a G, and this Hn is a normal subgroup of a H, and this Hn is a subgroup of a G. So there is a different things we have to just try to show that. Then we can say that this H over H intersection, this H is a you have a subgroup, and this is a clearly H intersection is a normal subgroups. So this means clearly this H over H intersection N is a meaning, and similarly H is a subgroup and N is a normal subgroup, and then this is again this is a meaning of this quotient group. We have to just say that into this form. So let us try to prove this. We have to because first we have to this set Hn, and we have to this is a subgroup of a G, so we have to show that this Hn is a subgroup of a G, and this H intersection N is a normal subgroup of G. Then we have to try to define a bijective homomorphism from H this quotient group to this quotient group, and this complete the proof in this sense. Okay, so let's start with the proof. With first we show that this H and H is the element of H and N is the element of N is a subgroup of a G. And now clearly you can say that H is the element of N. So clearly H is the you have a subgroup of a G, and then N is also is a normal subgroup of a G. So this N is a normal subgroup of a G. So this means clearly this set is a non-empty. You can say that He or En is the element of this thing. So clearly this set is we can say this simply Hn is non-empty because of this H is a subgroup of this G, and N is a normal subgroup of a G, and N is also is a subgroup of a G. So this means this is a subgroup, then E is the element of a Hn. So this means clearly H intersection N is non-empty. Now we have to take two different elements of this H1 N1 H2 N2 are the elements of a Hn, and then because we have a N is a normal subgroup and N is a normal subgroup of a G, then we can say that, and you have a this means H we have to H to the power H. This is H1 and H2 are the elements of a this is here is a H1 and H2 are the elements of a H, and this is clearly the subgroup of a G. So this is a subset of a G. So we take any element of a G. So this means N is a normal subgroup of a G. This means H2 inverse, and you have a N1, and then you have a H2 is the element of a N by the due to the N is a normal subgroup of a G. So by the normality of this we can say that, so this is clearly this is the element of a N, because N is a this is a N is a normal subgroup of a G. So now we take a first we show that the composition of these two again is the element of a this Hn. So this is Hn Hn1 Hn2, then this can be written as a we can write a H H1 and then we have to write this H2 inverse. This is nothing but is equal to H2. So this can be written in the form of this H1 identity N1, and then you have a H2 and N2, and in this place of identity we can write H2 inverse, and then we take a into this form, we take a H2 inverse, and then we have a N1, and then you have a H2, and then you have a clearly H2 inverse and as an element of N, and this is equal to, you have a clearly this is again is a N2. So this is the you have a H1, then you have a H2, and then this is the element of N, and this is also the element of N. So this is the element of a, this is completely belongs to the N, and then H1 and H2 are the element of H. So this means we can say that this H1 and H2, these two are the element of a H. So this means this thing, this completely is the element of a H of N. So this means this completely in the H of N, means we can say that clearly this H N is closed under the binary operation is this form. Now second we take inverse is also, so we take some H1, and we have a N1, and that is the if you take a inverse of this element, it also belongs to the this NH. So this is, we have to just say that this is the element of a clearly this, because this is the element of a N, and this is also the N. So this whole thing is N, and this is the element of a H. So this is completely is H N. Now inverse of this we can write in the form of this Hn ka whole inverse, Hn ka whole inverse, N inverse, H inverse, and now again we use the property of this. We take this can be written as a this we write E times of a N inverse, and we have a H inverse, and then in place of a E we write the H inverse, and then you have a we take a H, and then you have a N inverse, and then H inverse. Now that's again H inverse, then you have a H N inverse and H inverse, and H again is a normal subgroup. This is the element of a belongs to the N, and this is the element of H, because if you H is the element of H and H is a subgroup of a G, then H inverse is also the element of a H. So if S inverse is also the element of H, so this means this completely is the element of a, this is the element of a N, and this is the element of a H. This is completely the element of a H of N. So we have to show that if we take any two elements from H N, then there is a composition is again belongs to the N. If we take some elements inverse as belongs to the N, then also we show that the inverse of that element, if Hn is the element of a H, and then inverse is also belong to the this set. If also belong to the this set, then clearly we say that this H of N is a subgroup of a G. So now we have to finally show that this Hn is a subgroup of a this G. Okay, so now next we prove that the intersection H intersection N is a normal. So we have proved the H intersection N is normal in H. So we take any element of a H is the element of a H, and then element of a some element, suppose X is the element of a H intersection N. So we show that H inverse is the element of again H intersection M like this. So if we showed that this form, then we can say that this H intersection N is a normal in H. So let H is the element of a H and N is the element of H intersection N. If H is a then this is H inverse N is the element of a H. We call H is the element of a, this means this implies that N is the element of a H intersection N, then N is the element of a H, and N is the element of a N, and then now H is the element of a, you have a H. So if you have H is the element of a we have H is the element of a H, then H inverse is also the element of a H. This implies that you can say that, and by this property N is the element of a H intersection N. So if N is the element of a this, so we have to N is the element of a H intersection N. This implies that you have a N is the element of a H, and n is the element of a n, and then you can see this this h is n is the element of a h, and we have h inverse is the element of a h. So we can say that h inverse n and h, this is also the element of a h. So we can say that h inverse n, h is the element of a h, since each element of a h is n. Now we have to also, because you know that we have given the n is a normal subgroup of a G. If n is a normal subgroup of a G, then clearly this set H inverse and H is also the element of a n, because n is a normal in G and you have a H. Clearly this H is the element of a H, is subgroup of a G. So this means this clearly we can say that this is also the element of a same element. H inverse n is the element of n, since n is normal. So this means we show that this means H inverse n is the element of H, and H inverse n is the element of n also. So we can say that clearly this element is belongs to the H and also belongs to the n. So this means H inverse n, H is the element of H intersection n, and then we can show that clearly we can say that H intersection n is a normal subgroup of a H. So we prove that clearly H and R is a subgroup of a G, and H intersection n is a normal subgroup of a G. Now next our job is we have to construct a one bijective mapping from H to this form, and then we have to, if we define into this form, then we can using the first fundamental theorem of algebra, we say that H upon kernel of phi is isomorphic to Hn upon n, and then we have to show that this kernel of a phi is nothing but is equal to H intersection n. So we have to define a one mapping from H to Hn, then means clearly we have to if this is a bijective mapping is there, then by the fundamental theorem of first theorem of isomorphism is saying that this H over kernel of phi is isomorphic to this Hn over n, and then if it is this, then we our objective is show that this kernel of a phi is nothing but is equal to H intersection n, because H intersection n is a normal subgroup and kernel of a phi is always known. So now first we define in this this map from H to Hn by n, and then we have to show that H phi of H is nothing but is element of a, this is the coset. So this is H Hn, yeah, nh, this is, so we taking the element of a, this is equal to Hn, and now first we have to show that this the map this we have to define is a well is map is a well defined. So we take two elements H1 and H2 is equal to the same, and if H1 and H2 are the element, this H1 is the element of a H and H2 is also the element of a H, and then we have a n is a nothing but is equal to n is a normal subgroup of a G, and H is a subgroup of a G. Then we can just write this H1 n is the same as a H2n, and now H1n means you have a phi of H1 and this is a phi of H2. So this means we can simply say that this map we define is a clearly is a phi h is equal to Hn is a well defined map. Okay, so this is a well defined map. Now we have to try to show that is a, because is a onto homomorphism by the first isomorphism theorem. Is saying that now we have to show that this phi map is defined is a onto. So take any arbitrary element y from this set H. Hn quotient group of this, and y if is the element of this set, then y can be written as a Hn into n for some H is the element of H and n is the element of a n. But you know that you have this n, and n is nothing but is equal to you have a n by the because you have n is the element of n, then this implies that n is a normal subgroup. So this means n of n is equal to n. So n of n is equal to n, this means this is nothing but is equal to you have a n. So y is can be written as a h of n, and now y if h or f n is nothing but is equal to phi of h, we can write into this form. This means clearly we show that this map phi is also is a onto, and now we have to next step is showing that this map is clearly is a homomorphism. Okay, so now we have to try to show that this phi is a homomorphism, and then we take two elements h, and h1 belongs to the h. So this h and h prime is the element of a h. So phi of h now by the definition this can be written as a h prime n, and then h n prime n can h of n, h prime of n by the a b n can be written as a n, and you have a bn by the definition of a defined map of a quotient group. In the quotient group, we binary composition is defined an bn is equal to abn. So by this property, this can be written as a hn and n h prime n, and now hn is equal to phi h, and this is equal to phi of h prime. So we have to show that phi of h prime is the same as a phi of h and phi of h prime. So this means by this we can show that this phi is also is a homomorphism, and then if phi is also homomorphism, we show that phi is onto, phi is homomorphism, then is onto homomorphism. Then we can say that the first isomorphism theorem, the image of a phi is isomorphic to h of kernel of a phi, and that is h of n is isomorph is equal to phi of h, and then this is isomorphic to kh upon k phi. So image of a phi is nothing but is equal to, you have a h phi is this, because phi is you have a defined in the map of a h to hn over n, and then we have a this thing. So this means image of a phi is, now our job is showing that, because we have to show that this hn over n is isomorphic to h over h intersection n, and now by this theorem, that this means our job is this, we have to show that this kernel of a phi is nothing but is equal to h intersection n. So from this we have to find what is our this kernel of a phi. So finally we have to show that this clearly. So we take any arbitrary element in the kernel of a, so kernel of a phi is nothing but is equal to, you have h is the element of h, phi of h is equal to identity, because you have a phi is may have defined h to hn over n, and now you have a hn over n quotient group, and now identity of a this is equal to, you have a clearly is equal to n in this group, quotient group, and this is a, and then we have to say that kernel of phi of h is equal to this is phi of h is equal to n, and then phi of h is nothing but to h of n is equal to n, and now you have proved that we have by the coset property hn is equal to n, means this h is the element of a n. This is condition is a if and only if condition. By this we can show that clearly, if hn is the element of a is the same n, then h is the element, and now if h is the element of n and h is the element of a h, then h is, this is nothing but is equal to kernel of a phi is the same as a h intersection, and we have to taking the h is the element of h, and we have to show that h is also the element of n. That means h is this is completely nothing but is equal to, is kernel of a phi is nothing but is equal to h intersection n. So finally we have to prove that kernel of a phi is also h of h intersection n. So if kernel of a phi h intersection n, then we have to, theorem is saying that, so hn over n is isomorphic to you have a h over a kernel of a phi, and kernel of a phi, that means this is nothing but is equal to, you have a h over h intersection n. So this complete the proof of a second isomorphism theorem. So we can we've easily proved that, that means we have a, if we have a n h is a, we have a subgroup of a g, n is a we have a normal subgroup of a g, and we have to define the nh is the form of a this hn, such that this is the form of a hn, h is the element of h, n is the element of n. We show that this hn is nothing but is equal to is a subgroup of a g, and we have to show that h intersection n is a normal subgroup of h, and by this we have to define a one bijective function from this, and So we have to show that. This means clearly we have to, if we have to show this is normal, then this is the meaning, and this is also is the meaning. And finally we have to prove that this means if h n by n is isomorphic to h by h intersection n. So this complete the proof of this theorem. So now we have a simple example for based on this theorem. If we take a p and q be two positive integer, pz and qz are normal subgroup of a z, because you said that if set z is under addition is a group, and then you have to just say that mz or pz whatever this is again is a clearly if you take some any m, so mz is clearly is a normal subgroup of this z. This pq, pz and qz are the normal subgroups of z. And then by the second isomorphism theorem is saying that pz is a normal, and then pz intersection qz is normal into this pz. So we can say that this quotient group and pz plus qz over this, because is the coset is here, you have a in the form of a this form. Product this hn means we have a h plus n if you have a binary operation. So this is the coset is in the form of this form. So this we can write in this form. Then we have it, this is equal to qz. So this means are isomorphic. For particular, if we take a for example, we take a p is equal to 8 and q is equal to 12, then clearly we have a this is equal to pz intersection qz. P is equal to you have a, so you have a 8z intersection, you have a 12z is nothing but is equal to you take a is a 24z. And similarly if you take a 8z plus 12z, and this is nothing but is equal to 8 4 is 4. So clearly you have a 4z. And then similarly you can say that if this so 8z over 20, this is pz means 8z over this intersection is equal to 24z. So this 8z over 24z, and then p plus z qz is equal to 4z over 12z. And then we have to just say that is clearly this. So this means we can say that this 8z over 24z is isomorphic to 4z over 12z. So by this second isomorphism theorem, we can easily prove that this is if we have any positive integer, then this satisfied by the theorem. We can find that pz is and a quotient group of pz and pz intersection qz is isomorphic to pz plus qz over qz. Okay, now we have to just try to one more example in this form. Let I take a g is equal to z18, and h I take a in the form of this thing, because we have to you know that this in the form of this hn over this means we have to just using this we have to just say that into this form. Yeah, just you did just take this form. We have to just say that hn over n, and we have to just okay hn over n is isomorphic to h over h intersection n, or is this vice versa? So I just take a group of g is equal to z18, and h is a group is generated by 6. So generated by 6 is a subgroup of g under addition modulo 18, and then under addition modulo 18 there is a 0, 6, 12, and then again is 0. So this is 0, 6, 3, and n is I take a normal subgroup is which is generated by 9, and we take a 0, 9 and generated by under again under addition modulo 18. So 0 and 9 and no other element. So this means we can simply say that this clearly you can see this h is nothing but is equal to is a clearly subgroup of this g, and n is nothing but is equal to is a normal subgroup of this and similarly this g. And now by applying this theorem we have to calculate the hn and h intersection n by these cosets. So then we can just say that first we take a because hn means we have in this case our h plus n. So we take a h plus n, and then h is equal to this and n is equal to this. So we have to take a this is some cosets are there. 0 plus 0 is equal to 0, and with the 0 we have a 6 and 12. So we have a 6 and 12. Now by the 6 we have a 9, and then we have a 9, and then 6 plus 9 is equal to, you have a 15, and 12 plus 9 is equal to, you have a 18, 21, and by the modulo 18 is equal to 3. So clearly we have to taking the form of this h plus n is nothing but is equal to into this form. And now by these two you take clearly you have to just see the h intersection as is nothing but is equal to, you have a identity element. So intersection is identity, and now we have to just say that according to the theorem h by n, we have to take this factor group, and this factor group means we have to take a h plus n over n, and thus the cosets are of this h plus n plus n. So we have a coset of this is equal to, you have a h plus n and plus n like this type. So I just take a this n plus you have a n plus 0 and n plus 9 is, you have a getting the same is equal to this, and then we have a, I take a this h is equal to, you have a, and then you have a n plus h or h plus n. This is not a difficulty because, and then because this is group is a G is a abelian group. So n plus we take a 0, and n plus 0 you have to take a n plus 0 is equal to 0, 9, and now if you take an n plus 9, if you take a n plus 9, clearly you have a n plus 9 is equal to 0 plus 9 under modulo hetero, and 9 plus modulo hetero 9, and that is equal to 9, and you have a 0, and this can be written as also 0, 9. So this means n plus 0 and n plus 9 is the same as a 0, 9. Similarly, if we get n plus 3, and now you take a n plus 3, if you taking by this element as here h plus n is equal to this 0, 3, 6, 9, 12, 15. So I take a into this form, n is equal to, you have a this. So we take a n plus 3. If you take a n plus 3, you have a clearly you have a 3, and you have a 3 plus 19 is equal to 12. So this is equal to 312, and similarly if you take a n plus 12, so 0 plus 12 is equal to 12, and 9 plus 12, 21 is equal to 3. So in this in these two cosets the value is simply is equal to, we have a 3 and 12, and similarly if we take a this another element, we have to take 6 and 15, and then we have again is this we have a 6 plus 6 and 6 plus 9, and you have a 6 plus 9 is equal to 15, and now if you have 15, and then you have 15 plus 9, and then you have a 15 plus 9, you have just 24, and then again you have a 18 by 6. So that means we have to getting this value of this quotient groups are 0, 9, 3, 2, and 6 and 15. So now we have to find the coset again h over h intersection n, and the coset of this we can find in this form h intersection, because h you just say that h is equal to 0, 6, 12. So here h is equal to, you have a 0, 6, 12, and h intersection n you have a nothing but is equal to 0. If a 0 plus 0 is equal to 0, 0 plus 6 is equal to 6, 0 plus 12 is equal to 12. So that means we have to only, these are the cosets of this h intersection, this factor group of h over h intersection n is the these are the cosets are there. Now correspondence between we have this thing and h intersection n described in the proof of the second theorem. We have to define a bijective map. So we have a phi of h plus n to this thing h intersection this. So we have to just say that phi of where phi of h n plus n is the nothing but is equal to h plus h intersection n into this form. So we take a h plus n, 0 plus 0 plus n is equal to, and then we have a 0 plus same as a, you take a we have a 0 n plus 0 n plus 9. So this is 0 plus 9 plus n is equal to, you have 0 plus h intersection n, and similarly for this second one is a 6 plus intersection n, and the third one is this is equal to 12 plus intersection n. So this is, you just see this here, we getting the 0 6 and 0 6 and 12, and by these things we can write into a this form. And now just take, you have to, this thing is equal to, we have a all the elements of a, we have a 0 plus n, 9 plus n the same, 6 plus n, 15 plus n, and 3 plus n, and you have again is a 12 plus n is the same. So I take into this form, and now we have a this means phi is mapping into this form, 0 and 9, this is going to 0 and 3, and you have to just select 3 and 12 is going to, you have a 12, and then you have a this is 3 and 12, and the 16 and 6 and 15 is going to 6. So this means this way we can define is a bijective maps, and this way we complete the this explanation of a this second isomorphism theorem. So I think you have a clear to understand this result here. Okay, so let us try. We have to discuss one more example to clarify this. Here we take intersection is equal to identity, but we try to solve some different types of different intersection. We also continue for one more example for this related to the this. So we take a different example like this. G is equal to Z36. H is a subgroup of generated by 6 under addition modulo 36, and n is a normal subgroup generated by n9 under modulo addition modulo 36. So we take a h plus n. H plus n is, you know, just take a just take, you have to just h is the element of this, and n is the element of this. So 0 9 6 18 are there. Now 6 plus 9, and then all of them, so we have to just check verify into this form. We have a 6 plus 9 is equal to 15, and 6 plus 24, and then similarly all other elements are there. So you just check, if we taking a sum of these two, h plus n, we have a 0 3 6 and all this in the form of these. Now if we take an intersection of these two, and now this intersection is equal to 0 and 18 and 0 and 18, and that is, that means intersection is a two elements are here, 0 and 18 are the elements into this intersection. So now we have to clearly find all the cosets of this h plus n by n. The cosets of this is equal to, simply is equal to n plus 0. N plus 0 is equal to 0 9 18, and then we have to verify clearly into this form. We have a just you take a n is equal n is equal to, you have a this, and now we have to take a n plus this is the coset we taking is equal to h plus you have a h plus n, and h plus n you have a clearly here h plus n is equal to 0 3 6 and so on. And then we taking the this with the with n. So this means we take, if you take a with the 0, just one I just take a n plus 0. So n plus 0, n plus 0, n is equal to, you have a this. So this is simply is equal to this form. So this means we have to take a h plus n. So n plus 0, n plus 9, n plus 8, n 27 is equal to this. Similarly 3 12 21 and 30. So we have a, so in the sum we have to just take an element of a sum, is we have this is total number. So we have first one is equal to, you have a 0 9 18 27. So we have a 0 9, we have a like this. We have to take a 0 0 9, and we have a 18 and 27, and then we have 18 and 27. This is going to the with the this over n. So this we have to take a sum with n. So 0 plus 0 is equal to this. So this is nothing but is equal to n. So thus if you want, you can just check. I check as 0 plus n is equal to, you have a n, and now we have to take a 9 plus n. Yeah, so 9 plus n means we have a 0, and then you have a 9 plus 9, and now you have 18 plus 9, and you have a 27 plus 9. And now if you take a 9 plus 9 is equal to 18, so this means you have to getting 18, and then you have a 18 plus 9 plus sorry 18 plus 9 is equal to, you have a 27, and then 0, then you have a 18, and you have 27, and then 27 plus 9, you have a 27 on 36, and 36 you have a getting is equal to clearly this is 9, and then you have 18, and then you have a 0. So this is again we have to getting the n. If you take similarly for 18, if you have a 0 plus 18 is equal to, you have a 18, and then you have a 18 plus 9, and then you have 18 plus 9 is equal to 27, and then you have a 18 plus 18 is equal to 36 is equal to 0. Now 18 plus 27, and that is giving you again is a 9. So this means all the elements of it, this is giving clearly is equal to this is giving you a up to n. And similarly we take calculating in this form, this is giving you a this types of a cosets, and this is another set of coset is equal to this. We have a three different cosets are there, this one, and this one. So clearly we just try to find the coset of this h over h intersection n, and then they are 0, 18, this form. This simply again because in h intersection n you have a 0 and 18. If you take it with the 0 is the same, if with the 18 is also same, because under the modulo 36, then with the 6, and then with the 24, and n is equal to, you have h is equal to 12 and 36. So all the elements is giving here. So three different cosets are here. So now the corresponding this and this describe in the proof of the second isomorphism theorem, we can say into this form. So we calculate the this is equal to 0 plus h intersection n, and if we taking this is equal to 6 plus h intersection n, and similarly we have a 12 plus intersection n. And also, so this means we have a giving the three different things is there. This for n is mapping to 0, 18. Just take this form 0 intersection 18, and then we have a similarly you can just say that this set another cassette is mapped to 6 and 24, and this set is mapped to 12 and 30. So this means that means this complete the list of this cosets we can just find into this form. So that's clearly you have to understand the second isomorphism theorem. So we have to today we prove the second isomorphism theorem and also discuss these two examples of a second isomorphism theorem. Now I stop here, and in the next class we continue the third isomorphism theorem and try to discuss some other examples of the third isomorphism theorem. Thank you very much.